The first of many pre-recorded lectures that we'll have in AP Physics 2 this year, since we have chosen to do our notes in a remote fashion. Our first unit is going to be on fluids, as I've mentioned before. So this first topic presentation here is going to be Fluids 1, which is going to be an introduction to fluids and density. And I know that you all know what the word density actually means, but we'll spend a lot of time talking about it in the perspective of our fluids unit here, rather than what you might already know. Now let's talk about our learning targets. So I can identify states of matter. I assume that you can probably name at least 3 of those. I can define a fluid, and that word fluid is confusing to the general population, I would say, just for the fact that sometimes if you say the word fluid, people are going to think liquid, and that's not necessarily true. Liquid is a fluid, that's correct, but there's more to a fluid than just being a liquid. I can describe fluid statics versus fluid dynamics, and I know that you all definitely know how to talk about the word static versus dynamic. We spent a lot of time on that in our dynamics unit when we learned all about forces last year for the first time. I can define density. Once again, probably you're aware of the equation for density as being mass divided by volume, but we're going to take a look at what density means in the context of fluid mechanics. I can calculate the density of various objects. So again, it may be as simple as rho, the symbol for density, is equal to mass over volume, but it's not always that simple. We've learned that physics is very rarely that easy with that kind of equation. And then the last one is that I can construct graphs and linearize data, and I know that both of those are our absolute favorite things. So we will get to do a whole lot of that once again. So there are 4 states of matter. I know that you could definitely name the solid, liquid, and gas ones, and you could probably even tell me a lot about the properties of them, especially those of you who have had chemistry before. But there's 4 actually that are observable in everyday life, and that 4th one is plasma. But in this course, we're not going to discuss plasma. Plasma is a really interesting state of matter, but it has its own field of plasma physics that it abides by a lot more laws of physics that are well beyond the scope of this course. So, some things that you might already know about these states of matter is that solids are going to maintain both a fixed volume and a fixed shape, okay? So they cannot change shape, they cannot change their volume. Liquids are going to maintain a fixed volume but not shape. So whether I put a cup of water, whether it's in a cup, whether it's in a bowl, whether it's splashed all over the table, that can take on a different shape. However, its volume is always going to be fixed. Gases have variable shape and volume, so when the time comes, gases are a little bit more tough to understand as far as their molecular nature than something like a solid, which is predictable. And since gases and liquids both flow, they are collectively called fluids. So a fluid is something that flows. It's not necessarily just a liquid. Those 2 words are not synonymous when we're talking in physics. Okay, so both gases and liquids are fluids. So when water is a gas or a steam, the molecules are going to be bouncing off walls of the container. So we're going to take a look at this simulation here and see if that's actually true. So let's look at the states of matter. And let's look at when something's a gas. And we can see that, yes, in fact, these molecules are bouncing off the walls of the container. Let's instead look at when it's a liquid. You can see how there's a much more condensed volume, and the liquid its molecules are not moving nearly as rapidly. And another thing to note is that the molecules are going to fill the container from the bottom up. While they're moving around. You can't pour water into a cup and the water is just at the top. That probably makes sense, but you can see that some of those molecules are going to rise up, and we do talk about that. That's probably what you know as evaporation. And then let's take a look at solid. In solid, you can clearly see that the molecules just vibrate around, but for the most part, they are pretty much stuck in their general position. Okay, so let's go back to our slideshow here. So by definition, a fluid is a substance that is actually capable of flowing and takes the shape of its container. So if we have some kind of, once again, a cylindrical container here, the liquid is all going to be at the bottom, the gas is going to be moving around quite a bit, but you would agree that both these things are fluids because they do flow around their container. Okay, a fluid is made up of many tiny particles, and so we can actually treat a fluid as a system of objects in the same way that we have talked about systems of objects before. So the macroscopic properties of a fluid are going to be determined by the properties and interactions of the particles that actually make them up. So it's the individual properties of the molecules themselves that define what this gas or liquid ends up being. So some attributes of fluids. All fluids are going to have mass, they're all going to have volume, they're all going to have density, and they're all going to have weight. Now with this in mind, we're also going to make a couple of assumptions here, and it's very important to remember these assumptions. So liquids, we'll start with, they are going to have a constant mass. We're going to assume that there is no evaporation in a liquid, otherwise this gets a lot trickier. So for the purpose of AP2, liquids have a constant mass, okay? They have a constant volume, which a fancy way of saying that means that they are not compressible. Okay, so constant volume means non-compressible. Non-compressible flow, or incompressible flow, you may have heard it called before if you've heard that word at all. Constant volume. They have a uniform density. So if I take a drop of the water out with a pipette, that drop of water is going to have the same density as any other drop of water that I take out with a pipette from that exact same cup. And then they're going to take the shape of their container from the bottom up. We are not assuming that they flow into, that liquid molecules flow any other way other than from the bottom up. Okay. Gases are a little bit trickier. Just the first thing that we are going to assume is that they have constant mass, so they're not leaking out. If gas is leaking out, that's extremely unpredictable, and we can't do anything as far as calculations go with that because we don't know what's escaping, we don't know how it's escaping. There are just way too many variables involved in that. So we're going to assume constant mass. So for both fluids that we are talking about, we're going to have mass conservation, and that will become extremely important in a lot of the equations that we learn. They have variable volume, which means they're compressible. Okay, so we talked about having a constant volume, that means not compressible. If they have variable volume, that means they're compressible. They're also going to have variable density, okay, also means compressible when we talk about uniform versus variable density, okay. And they're going to fill the container and therefore also take its shape. So if they are in a container, we can assume that they are taking the shape of that container. So if we put a bunch of gas molecules into a cylindrical container, they take on the shape of that cylinder. Otherwise, we have no idea what shape they're taking on if they're just in the natural air, like where you're sitting right now. Okay. Let's talk a little about statics versus dynamics. Once again, we're talking about fluids, which does not necessarily mean liquid. This is the case for both gases and liquids, so any fluids, okay? So when we talk about hydrostatics, fluids are going to be at rest. So some examples that are very often talked about are water sitting in a glass, helium trapped inside a balloon, a wooden log that's floating in a pool, some series of liquids at rest in the same container, a coin that is slowly sinking to the bottom of a jar filled with fluid, and we'll talk about that, or an air bubble rising to the surface of the ocean. So both of those things we're going to talk about as far as being hydrostatic, because you'll make the argument that those things are actually moving, but when we think about statics, what does it mean to accelerate versus to be in static or dynamic equilibrium? Okay, so fluid dynamics is concerned with the fluids that are actually flowing like water traveling through a pipe. So we call this hydrodynamics. So for the AP2 exam, we're going to end up calculating what happens if a pipe changes its diameter or goes up or down a hill when fluids might change speed, undergo pressure changes, etc. So we're going to look at a lot of that when we talk about different things that are with regards to hydrodynamics. We'll look a lot at energy and mass conservation of flowing fluids as well, which I did mention before. So if mass is conserved, there's a lot that we can do with that and kind of extrapolate to other things. Okay, so we're going to take A quick break here for a question. So which of the following attributes distinguish fluids from solids? So first one here is being made up of atoms and molecules. Well, we know everything is made up of atoms and molecules. Taking the shape of their container. Well, that's a pretty good answer, so we'll come back to that. Being compressible, changing density. Now, here's the thing. Fluids, whether it's liquid or gas, might be compressible. We're making the assumption that liquids are incompressible, so this cannot be the answer. If this just said gases, then this would be a viable answer, but it does not. And then are not affected by gravitational fields. So we said at the beginning that these states of matter are going to have a bunch of different attributes, one of those things being mass, and as long as something has mass, that means that it's going to be affected by a gravitational field, as we learned in AP Physics 1. So taking the shape of the container is the only adequate answer here. Okay. We'll do another example here. So which of the following assumptions are we going to make in order to solve problems? So this is basically, have you been paying attention to me? Liquids conduct electricity. I have not mentioned the word electricity yet, and I won't for a very long time, so you can rest assured that I eventually will, but not anytime soon. Gases cannot be compressed. I did mention that we are talking about gases in terms of compressible flow, both as far as their volume is concerned, as well as their density is concerned. A particular fluid sample has constant mass. I absolutely said anything that is going to, any fluid itself, whether it be liquid or gas, is going to have constant mass. And there is no atmospheric pressure. Now, I haven't talked about atmospheric pressure yet, but I will talk about that. So as long as we're talking on planet Earth, or any celestial body that has an atmosphere for that matter, there is going to be some kind of atmospheric pressure. And so we need to make the assumption here for all of the fluids problems that we do that a particular fluid sample is going to have a constant mass, okay? That's going to be a key assumption when we are solving problems that are involving liquids and gases, because we cannot do anything as far as calculation or understanding goes with regard to their leakage or evaporation. Now, you may have a multiple choice question that asks you about leakage or evaporation in terms of like, which of the following is not an assumption that is made or something. You know, AP will ask it in a much more eloquent, wordy way, but just to keep that in mind, that leakage and evaporation are not unfair things to ask about, but you should be very aware that those are things that we assume do not happen if we are explicitly stating that mass conservation is a thing, okay? So let's start talking about some actual fluid stuff now. So I'm going to give you a second to think about this. And what weighs more, a pound of feathers or a pound of bricks? Okay. The trick here, and this is kind of a tricky question, I'm sure that some of you have heard it before, is that this says this is a pound of feathers and this is a pound of bricks. That means that they weigh the same because they both weigh a pound, okay? That is one of the only times, as you know, that you are going to see the word pound in these presentations. Talking to you there, Colleen. So the next thing that we are going to talk about as far as density is concerned, so let's say we have a log, okay? Sometimes people are going to say that iron is heavier than wood, but let's think about a giant wooden log, okay? That giant wooden log is definitely going to be a lot heavier than a small iron nail. However, that log will float in water while the nail would sink if you were to place both of these objects in water, if you thought about it. What we really should say is that the iron is more dense than the wood. So this is not a matter of weight, this is a matter of density. Okay. So density is of an object is its mass per unit volume. And once again, I know that we have an equation for this. Let me write down the equation here. We have rho is equal to m over v, where rho, some of you already know this is density. I know that in middle school they may have just called it d. We are no longer in middle school, so we will learn our very fancy Greek letters. And I know that we did some things with density last year, especially in some of those problems in gravitation So I know that we do have a general understanding of what density is. And then V is going to be volume, okay? One of the tricky things here is that sometimes you're going to get a density that's measured in grams per centimeter cubed. Now we know that's not the SI unit that we are very used to. We're used to seeing kilograms and meters cubed, but sometimes you will see it measured in grams per centimeter cubed. So liquid water is one that we're going to refer to a lot. So liquid water at standard temperature and pressure is going to have a density of 1 gram per centimeter cubed. So sometimes you might hear, oh, what's the density of water? And someone gives you an answer of 1. Now that's not completely untrue, but you have to understand what they mean when they say 1. They're talking about 1 gram per centimeter cubed. Okay? That means that 1 liter of a water bottle contains a kilogram of water. And a cubic meter of liquid water is going to have a mass of 1,000 kilograms, which is about the mass of a small car. Okay, so we'll talk about how we're measuring water and the different units that we could actually measure it in. So once again, the same mass of feathers and bricks is going to have very different volumes. So we did talk about this pound of feathers versus this pound of bricks. You would need a whole lot more feathers in order to weigh a pound than you would bricks, because bricks are significantly more dense, okay? They have a small volume, but their density is quite large. And so when we look at this equation, that makes sense. If you have a small volume, density is going to increase, as opposed to when we're talking about this pile of feathers here, the mass that's required to get this weight of feathers to equal that of the bricks is significantly greater. So when we think about experimental design, I know those are also two of our favorite words, besides linearized data. So one's going to have to determine the density of an object or fluid experimentally. So we are going to do a lot of practice with this, but I figure we could talk a little bit about it now as far as going back to our learning target about how are we going to create graphs and linearized data. So to determine the density of the object, you have to know mass and volume when we're talking about a fluid, okay? That's going to be a bit different when we talk in terms of thermodynamics in our next unit, but for the most part right now, as far as figuring out density goes, mass over volume is going to be your friend. We measure mass with a balance, a spring scale, or an electronic scale, as you've all learned in AP1. And you're going to measure the volume by measuring the sides or the radius with a ruler and calculating based on its shape. Okay? So that's how we measure the volume of the particular thing. However, we do know that not everything has a nice shape that we're able to calculate the volume of, okay? However, you can get its volume by water displacement. So if I have an empty graduated cylinder here that has a volume of 150 milliliters, and suddenly I put in this nail here, or this bolt rather, that increases the water level, then I know that this object must have a volume that would cause this increase, okay? So if this is at 180, we would know that the change in the volume is 30 milliliters here, okay? And therefore, that would be the volume of the bolt. So when we talk about density, once again, so let's say you wanted to determine the density of clay in your lab. You could mold it into a cube and measure the sides with a ruler. But if we want to minimize error, remember our fancy thing here, multiple trials with a variety of side lengths, repeat, right? Repeat a bunch of times to reduce experimental error, and make sure you're weighing the clay each time. So this is just kind of to get you back in the idea process of how do we actually do experimental design. But if we do take a look at this graph here, this is a very not linearized graph. Now that's not necessarily a bad thing if the data does not call for linearizing. But we can talk about what it actually looks like to linearize our data. So we can see here that mass is on the y-axis and side length is on the x-axis. Now, because we have a little bit of experience with this, if we're calculating volume and we're trying to find the density from this curve, this graph is really not going to help us. But we do know that density is equal to mass over volume, right? Now, if I have mass here on my y-axis and I want to rearrange this equation such that mass is on the y-axis as a function of side length, I can say m is equal to rho v. And that works out because if I graph this, if this is y and this is x, then this would be my slope. Now, me graphing v is not the same as me graphing my side length. If anything, v is going to be equal to my side length, call it s cubed, in the case of my cube here, right? So what I need to do is actually graph mass versus volume such that I don't have this cubic function that I would have to figure out the density from, okay? So if I go on to the next part here, so once again this graph is okay, but if we linearize it, we can use the slope of the line to determine density, as I showed you before. I'll move this out of the way so that you can see it. I know it's on your paper, and I did talk about it a bit on the last slide already. So if you plot the mass on the y-axis versus length cubed on the x-axis, that graph becomes a straight line with the slope being equal to the density. This is a much easier thing to figure out the density from, as we are very familiar with having linearized a bunch of data last year. Okay. So tips for graphing, in case we forgot, you're going to choose good units. You fill the entire graph up. You're going to include a line or curve of best fit, whatever's called for, and I promise we'll do tons of examples on both because I know how much we like doing examples of things. Calculate any important slopes. So in the case of what we just did here with our cube, the slope there was going to be the density of the cube, which is ultimately what we were looking for in our experimental design problem. So it's very important to actually measure the slopes that we're trying to measure and make sure your axes are labeled, which I know that I try very hard to make sure that you guys all do, and you guys are good about it, so just to keep that in mind. So let's do a couple more practice questions. So let's talk about this. So the density of a substance is rho, its mass is m, and its volume is v. If the volume of the substance is tripled, what is its new mass? So we're saying rho is equal to m over v. And now all of a sudden we have some rho prime, this new... I apologize. We're saying the density is staying the same. We're just tripling the volume. I apologize. So we have this density that's still staying the same, but we have some new mass that it's going to take on as a result of us tripling our volume. Now, these two need to be equal to each other because, once again, it's maintaining the same density. So what I do here is I say, okay, m over v is going to be equal to m prime over 3v, once again, because these two densities are equal to each other. If it's the substance, the density is not going to change. It's just mass or volume that's going to change, depending on what I'm doing to either thing. So if I look here, I could say, okay, volume is going to cancel out because I know that I'm tripling the volume, your rule of ones, as some of you like to call it, and that means that if we are going to maintain the same density, then we need to triple the mass. Now that might have been pretty easy to just figure out just by looking at it, but I did want to go through the process of ratios because a lot of the times I know that we might struggle with those ratios, and they are going to become very important, especially in thermodynamics. So which is denser, a cube of concrete with sides of L or a cube of concrete with sides of 2L? This is actually a trick question because they're made of the same material. So if they're both made of concrete, that means that they have the same density. Okay. You may be tempted to say the side of 2L or the side of L because you're saying, okay, well, volume's increasing or decreasing by this much, so what happens to density as a result? But ultimately, if the two objects are made of the same material, they're going to have the same density. So liquid X has twice the density of liquid Y. One student's experiment needs samples of X and Y that have the same mass. So what needs to be true about their volumes? So we're trying to figure out a relationship between the volumes of these two liquids that have different densities, okay? So we're saying that they have to have the same mass. So mass here has to be equal to each other. And we know that mass is equal to rho v. And we're going to say, okay, same mass here, right? So let's talk about X and Y here. So liquid X has twice the density of liquid Y. So that means that liquid X's density equals twice liquid Y's density. So here, let me back up a little bit. I'm not going to write that just yet. I will eventually. So this is going to be equal to the density of X times the volume of X, okay? And then the mass for Y is going to be equal to the density of Y times the volume of Y. And you could put subscripts in here if you would like for X and Y, but we do know that ultimately MX has to be equal to MY because of what we are told in the problem. Okay, so that's a consequence of that right there. So if I set these equal to each other, I could say, okay, well, rho X Vx is equal to rho Y Vy. And that's important because, once again, the masses are going to be equal to each other. I can now put this relationship in so that I can see a relationship between these volumes here. So I could say, okay, 2 rho Y Vx is equal to rho Y Vy. And now I can cancel out this rho y because I don't know anything about the densities other than that one is double the other. And I could say, okay, then 2Vx is equal to Vy. And that is answer B on our thing here. Okay. So you are given a wooden ball with a density of rho and a mass of m and a volume v. If you're given another ball, once again made of the same material but radius is doubled, what is the mass going to be? So, okay, we need to think about this because we know that the volume is v, however, we talk about radius being doubled here. So the initial reaction might be to select answer A, but that is not the correct answer in this case because we're talking about the radius being doubled. So we're saying, okay, we have v, and we're told that it is a wooden ball, and I know that we all know the volume of the sphere. So 4/3 pi r cubed, right? So that means if I double radius, my new volume, v prime, is going to be equal to 8 times my original volume, not just twice it, because I'm putting in a 2r cubed here, such that this is 4/3 pi 2r all cubed, which then becomes 32 over 3 pi. I just cubed the 2. 8 times 4 is 32 r cubed. So now I can see a little bit more clearly that the difference between these is a factor of 8, right? So that's how I got this relationship here. Now, I'm told that they're the same material, so I know that means that they have the same density. So I could say, okay, my original density was rho equals m over v, and I want that density to be the same, just with some m prime that I have as a result of doubling the radius of one of these balls. So if I have rho is equal to m over v, that's also going to be equal to m prime over 8v. Based on this here. Okay, and the fact that these balls, once again, have to have the same density because they're made of the same material. So I can cancel out the v's, and very similar to the last one, I just arrange and say, okay, m prime is equal to 8m. Okay. A container of water has a mass of 5 kilograms. What is the volume of this container in cubic meters? This is actually very nice because this is already in kilograms, so we can talk about that. So I know that the density of water in SI units, which I did not mention before because I knew that we were going to come to this problem, is 1,000 kilograms per meter cubed. And if you really want to do that out with the dimensional analysis, by all means, I encourage you to, but you could just remember it. In SI units, it's 1,000. In grams per cubic centimeter, it's just 1. Okay, so here we are also given mass, and once again, we're told that it's water, and all that we're looking for is volume. So I know rho equals m over v, which means that v is equal to m over rho. So that's 5 kilograms divided by 1,000 kilograms per meter cubed. So those units work out. The kilograms cancel. The meters cubed comes up. This ends up being 0.005 meters cubed when you put it in your calculator, or you just move the decimal place 3 places to the right because you're dividing, 3 places to the left rather, because you're dividing by 1,000, and you should end up with answer A. If you do have any questions, I encourage you to either message me on Schoology or you can comment on this video directly.